I would like to thank the organizers for inviting me to this workshop. It is really a pleasure to be here, probably because I think I'm going to learn a lot more from my experience here than what you'll probably learn from me. But nevertheless, I'm really very glad to share with you some of my experiences. And so being a chemical engineer, being not a mathematician or a statistician, this topic of interface between statistics and optimization is nevertheless extremely important to me. And I wanted to share with you some of the things we've been doing over the last few years in this area from a chemical engineering perspective. So first thing I'd like to do is I'd like to recognize the, there we go. Recognize my co-authors who have really done most of the work, Yajin Wang, Weifeng Chen, and Isu Ni, who have been either collaborators or PhD students or former PhD students. And what I'd like to talk about is this topic of model discrimination and parameter estimation for reactive systems. Now, this is what I would not call, cutting edge work. This problem has been around for a long time. But nevertheless, there are some new optimization tools that we're applying, and it's a problem that is still extremely important and I'd say can be done better. And so what I'm going to do is I'm going to talk a bit about an introduction, give you the how of this problem, which is the tools that are required for model building and for these tasks of, for building the model and validating it. And so I'll talk a bit about direct transcription for representing the reactive system. I'll talk about parameter estimation and nonlinear programming, and then talk about inference and nonlinear programming sensitivity. Then what I want to do is I want to talk about the what. And I've got some industrial case studies that will give you some idea of the scope of the problem, some of the challenges, and basically how we struggle to overcome them. And then what I want to do is talk about the why. And this was a very fortunate circumstance for us, because we could see why we do this in practice and what it really means in terms of doing this problem right. And then finally, I'll summarize and conclude. So the industrial examples are with some large research sponsors, large chemical companies, and it was really instructive to learn about how they do things and what kind of impact they have. So to get started, what I'd like to do is start with this idea of model building and talk about the formulation of first principles models. Now, I want to make that distinction versus what we talked about here, what was discussed here at this workshop, mostly data-driven models, okay, involving large sets of data, and then using that to develop these empirical models with many parameters, okay? And the idea of having something so large and fitting so many parameters that you have to use special techniques. Our models are not that large. We do have a lot of data. But our problem is not so much that we can't handle the data, it's that their data aren't very good, okay? And so we'll talk about that. The second thing is this idea of model validation and model discrimination, which I want to go into. And the whole point about this is developing predictive models, okay? Because what we want to do with these models is we want to use them for control. We want to develop optimal reference trajectories, and we want to do real-time optimization, let's say in a chemical reactor, in a chemical plant. And then for operations, what that means is this unit here is only one unit that goes over here, okay? And then there's a whole process built around it where you have to schedule operations, where you have to control utilities, where you have to worry about upsets and supply and demand from different parts of the plant. And that unit has to be able to interact flexibly within all those demands. So that model, basically the accuracy of the model and the robustness of that model, the solution of that model is extremely important if you want to exploit all of those decisions. So this is primarily getting a model for decision making. And now what we're going to talk about is what we mean by a first principles model. Okay, this is a model that is based on physics. So the joke is, the scientist wants to study nature and builds machines to study nature. The engineer studies nature to build machines, okay? And what a model means to a scientist is something, that really is supposed to describe fundamentally what's going on. That's the idea of first principles from physics and chemistry. Engineers have a slightly modified view, which is basically being able to have a predictive model that can extrapolate something you have not observed yet, but you need to use that to make decisions. So whether it really describes what's going on in nature or not is secondary to having this decision-making capability. Nevertheless, what we do in building these models is we have to apply conservation laws. The gaps in the conservation laws are filled in by constitutive relationships that come from independent studies at smaller time and length scales. And then what you want to do is you want to assess all those assumptions that you make in the model, adjust for missing information, and then you have to do parameter estimation, model building, and model validation. And part of this activity is strongly focused on optimization tools, and whether this model is right or wrong depends on whether it's going to work with decision making. And it's good to keep in mind the following quote, okay, from George Box. And so that's one that we keep in mind all the time. Okay, so this is a work process that I took off of this program in Europe at Delft University, which basically starts thinking about how one develops these models. And the first thing is to think about the fundamentals, starting from very detailed calculations at the atomic level, moving up to something at the molecular level, and eventually developing kinetics and thermodynamic relationships. That goes into constructing the reaction network and the rate expressions, and then initial parameter estimates over here. From there, we incorporate that into a reaction system, and this is where we see the optimization tools that we need to apply. We do the model discrimination as well. Sorry, there should be an arrow here. And then, based on whether that's done well or not, we may have to redesign the data and obtain more data to improve on this cycle here. Once that's all done, we have uncertainty quantification to see how this extrapolates to the rest of the world. Okay, the key thing here, though, is the models that we have, they mean something. They're supposed to describe some phenomenon, and the parameters that we get, they also mean something, okay? And so this is basically why we pay attention to these things, and we have to do not just the parameter estimation, but a lot more. So what we want to do is we want to figure out a way of working on this work process and handling good tools, integrated data, and then worrying about an interactive user interface. Okay, so this is basically the idea. But I want to talk a bit more about the tools. So let's talk about this. Ultimately, this problem is a dynamic optimization problem. Think of it as an optimal control problem. And in particular, what we have here is differential equations, algebraic equations, differential states, algebraic states, maybe some control profiles, but that comes later. And then finally, what we have is parameters P, okay? And those are the ones that we need to deal with as decision variables. Okay, now the first question is, how do we solve this? Well, one of the things about reactive systems that becomes very important is that they are frequently open loop unstable rather. And so if you put in a certain set of parameters, you might not get this to line out at steady state. This could actually blow up. And so what we want to do is use that well-known principle of thinking about boundary value formulations rather than initial value formulations, okay? This is written down as an initial value problem, or can be, and frequently treated as such, but if you want to embed that within an optimization problem, it's really good to think about that within a boundary value formulation. And so this is where we use direct transcription. What we do is we discretize the profiles, the differential algebraic equations in time, using an implicit Runge-Kutta discretization, a Gauss form, in this case orthogonal collocation on finite elements. And so what you see here is this form here where we apply this at finite elements. We have collocation equations that look like this, and we have polynomial approximations in each element, piecewise polynomials. For the differential states, the algebraic states, we actually don't enforce continuity between the elements. We don't need to. And if we have control profiles, then in that case what happens is, again, we don't enforce continuity between the elements. So this is basically how we take our DAE problem and turn it into a fully algebraic problem. And then what we have to do is solve a large NLP. Okay? So this is what the nonlinear program eventually looks like. Everything is discretized. And now we assemble that and look at the problem that you have on the right. And I know this comes as a disappointment to many people in this room. This is a non-convex problem. It is quite hard to solve. We are happy with local solutions and we use local solvers. But fortunately, if those local solvers give us solutions quickly, we can examine those solutions, usually get some insight to get very good solutions. So that's about the best I can say about that. So given this problem, how do we solve it? Well, what we like to do is we like to use a barrier approach. This problem is, I would say, mid-range. Probably the largest instance of this problem that we traditionally face is, maybe 1 million variables. Okay, and so we are happy to solve problems on the order of several tens of thousands or hundreds of thousands of variables, and that's usually a good size for us. The number of degrees of freedom in parameter estimation, or number of parameters, tends to be much smaller, something like 100, although we can certainly expand that quite a bit with certain classes of our problems. So that's fine. So in that case, how do we solve it? Well, what we do is we go back to this problem, and what we'll say, okay, take that problem, I'll simplify it just a little bit to make sure it's just non-negativity, although that just makes the derivation easier to write. And now what we'll do is make it a barrier function. Okay, and this was talked about yesterday by several people, Michael Jordan in particular. And so what we know, and this is going back to Margaret Wright's talk, is a very old result. It's in the book by Fialko McCormick, but actually goes back to the mid-50s, forming this barrier function, solving this problem instead of that problem for a fixed mu. And then if you solve a sequence of these problems as mu goes to 0, then what happens is the solution of this problem under mild conditions converges to the solution of the top problem. So that actually is well known. And it's a property that we use. Now, why is this important? Well, it turns out if you write this problem in a primal dual form, okay, then you can write the optimality conditions of this problem like that. Okay, you introduce a variable nu, which is kind of the pseudo multiplier here. These turn out to be the KKT conditions, or the KKT conditions of the bottom problem. And you see where mu appears here. Once mu goes to 0, they become the KKT conditions of the top problem. So that's actually a nice thing. So now when we solve this thing, what we're going to do essentially, and there are many details here I'm going to leave out, we solve this with a Newton method. Okay, so those are the conditions. If you write down the Newton step here, there's the Jacobian of those above equations, and those are the variables. Because these are diagonal matrices and they always have positive elements, then what we can do is we can eliminate the bottom row here and the last variable vector, and what we end up with is a very nice symmetric indefinite system. Okay, this is the key, the most expensive step in the algorithm. Okay, so we solve this problem with an LBL factorization most of the time. It's a very sparse system. There are nice things about that form, and of course, if you know something about the structure, you can handle much larger problems. So this is what was embedded in the IPOPT code. This is a code that was written by Andreas Wächter, one of my former students, who's now at Northwestern, and I'm very happy to say that this was written 15 years ago, still widely used. There's a nice community that uses it. It's open source. And what's interesting about this is what we can do with these kinds of systems here. So let's take a look. What are the benefits for parameter estimation? So let's see how that applies. First thing I wanted to let you know is that KKT matrix, well, the way we know that this is well conditioned and converging to a good local solution is by looking at the inertia of this matrix. Okay, the number of negative, positive, and 0 eigenvalues. Okay, so we know that the inertia of that matrix has to have this, and a number of positive eigenvalues is n, the number of variables. The number of negative eigenvalues has to be m, the number of constraints. And if that inertia is not correct, the LBL transformation will find that out. Okay, this is a nice result from Nick Gould. And what you do is you regularize that matrix with delta 1 and delta 2. And eventually, with large enough values of those two parameters, you will get the right inertia. Okay, and you can take the Newton step. Now, the key thing to notice about this is that inertia, which if delta 1 goes to 0, then then you have primal variables that are unique at the solution. If delta 1 and delta 2 both go to 0, then both the primal and dual variables are unique. So you satisfy these properties of LICQ, linear independence constraint qualification, and sufficient second order, strong sufficient second order conditions. And what's nice about this then is that in the context of parameter estimation, you have unique parameters. In other words, the data that you have are sufficient that you can observe those parameters, at least locally. Now, this is essential because the model that we want to develop is predictive, extrapolative, right? So if you have non-unique parameters, that's not going to work, right? If you have non-unique parameters that lie in some subspace, then those parameters really don't mean very much. And they have huge confidence regions, well, infinite confidence regions, that mean that you really can't use that model, you can't trust that model to predict things. So this is an important thing that we look for when we do parameter estimation. And then finally, if you take the sensitivity of this solution, and there's a quick way to calculate that, then you can get a reduced Hessian very quickly that will be used for confidence regions. So this is what we show. Here, if I take the parameter estimation problem here, take a look at the top problem here. What we've got is our data, y hat. Our parameters are theta. And let's just say I have a small prior for the theta over here. And so in that case, what happens is, if I look at this problem, what I'm going to do is I'm going to take a look and see that over here, this problem here, okay, is going to form this KKT system over here, where this is just the Lagrangian of the elements over here. Okay, now if I take a look at that problem, one of the things that happens when the data fit the problem very well, the model fits the data very well, is that you can see from the right-hand side that the estimates of the Lagrange multipliers actually go to 0. Okay, and you can even say, well, the expected value then would go to 0. And so in that case, I can look at this problem and simplify it just a little bit, okay? And so the off-diagonal elements on the Hessian are gone, and in fact, the elements, diagonal elements of the Hessian actually become those nice matrices Vy and Pi theta inverse. And now let's take a look at what happens if I introduce perturbations in the data, okay? If I introduce those perturbations in the data, then what you find out is I can now calculate delta theta as a function of the perturbations in the data, and that way I can obtain the covariance, all right? And so the covariance is actually going to be equal to the reduced Hessian over there, and that we'll call that V theta. And then the last two things are just a couple of definitions. What happens to lambda? It should go to 0. Or at least the expected value should go to 0. And then, of course, Z is going to be our null space of the nabla C transpose, or del C transpose. Okay, good. So with this idea, what we can actually do is say, great, we have a relationship where we can approximate the covariance of the estimated parameters by the reduced Hessian of the solution of this problem. And it turns out you can show this in about half a page of algebra, but more importantly, you can get this reduced Hessian, at least one particular instance of it, by taking this system, replacing the right-hand side over here by 0 here, identity here, and solving that system again with n theta backsolves, okay? And that gives you the reduced Hessian directly. So this is actually a nice thing. We've implemented that in IPOPT, which I was glad Margaret Wright talked about. Okay, so those are the kinds of things we have with sensitivity. So now, having that, you've got the covariance matrix, and we're going to use these approximate elliptical confidence regions to get an idea, not so much of the actual confidence regions of the parameters, but something that will allow us to screen which parameters are very well estimated and which are not, okay? So we all know that these elliptical confidence regions, they work for linear models, they work for the usual normal, unbiased distributions, which we're happy to assume. We know that for nonlinear models, these are an approximation, and often a poor approximation. But nevertheless, we're going to use them because they're easy to calculate, and we can use this for parameter screening, okay? Especially because we know that nonlinear confidence regions are much more expensive to calculate. Okay, good. So now what do we do with model discrimination? Now this is kind of interesting. What we're going to find out in the case studies is that there are going to be families of different models, okay? You can conjecture and postulate different models, okay? And so there's a maximum likelihood form, a Bayesian form, where we can say, okay, I've got this family of candidate models, MJ, okay? And they could be rate controlling mechanisms, slow reactions, competing models mechanisms. And one usually uses some kind of Occam's razor approach, okay? I think Bernd Sturmfeld's talked yesterday about AIC and BIC and different ways of trading off the likelihood function with the log likelihood function with the number of parameters. These are useful, but part of the problem is, as Bernd said, you still have to embrace this idea of singularity. And also, if you can get rid of singularity and get unique parameters, then you can actually hope to use them in some sense. However, there still is this issue, which one do you want to use? And we've adopted this idea of this Bayesian model that was developed by Warren Stewart and actually George Box as well, where what is done is calculate a probability share. Okay, and so what you have is you have a Bayesian quantity that is the probability of the model itself, given that you have estimated the parameters correctly and you have certain data. And then what you do is you take the probability of each of these models and calculate what the share is of each model. Okay, so it doesn't tell you that this is the absolute perfect model, but it says among the models that you examined, this is the most likely one. Okay, so we're going to use that idea. Okay, so those are the tools that we want to go into. And now what I would like to do is talk about some case studies. So let me start with the first one. The first one was a problem that was given to us that I thought was kind of difficult and unusual, and it is. This is a process that makes a herbicide. Okay, so if you're familiar with herbicides like Roundup and Lasso that you put on your lawn, this is one of those, okay? And so what you do is you basically say, okay, I have this solid-liquid reaction. You actually put together a liquid reactant, you put in a salt, and you put this in an organic solvent. And now what is happening is this guy is going to react. We have this reaction going on, the solid and the liquid forming another solid and another, well, actually two more solids. And the question is, how does this happen? It happens in a stirred tank reactor. And how do we come up with a model that describes the reaction mechanism? Well, this is pretty tough because you've got multiple phases involved. So what we're going to do here is we're going to start this way. We have issues, for example, what are the mechanisms that go on during the reaction? Not just reaction, but dissolution, diffusion, etc. We have different particle shapes and sizes that determine the reaction surface. And then we have to figure out how do the products actually form. Okay? So let's think about this problem. We looked at this, we came up with two general competing mechanisms. The first one is to say, okay, we have the liquid diffusing onto the particle surface, okay, and it's going through a film, all right, some boundary layer, and then it's going to form and react on the surface with the solid particle, okay. At that point, because it's not a porous particle, it actually forms on the surface and eventually it's going to crack off and the size of the particle depletes as the reactant forms into product. Okay, given that that happens, okay, then what you can do is you can write a mass balance for the solid and for the liquid species, okay, and in particular what you have over here is you have the surface, you have the surface area that's determined by this quantity here, and over time, now you can see as the species starts shrinking, the solid species starts shrinking, you basically have this thing getting smaller, and A is a shape factor, and then the second term here is the reaction rate, okay, and that reaction rate, okay, that's basically what happens on the surface. So you have the simple idea of a reaction rate multiplied by the surface area. Fine. Okay, so good. Now, there are several parameters embedded here that I'll go through later, but the point is you need to basically look at that surface reaction rate and then monitor the surface area and concentration. Now here's the competing mechanism. There's a salt particle here that's in an organic solvent, and there is a tiny amount of salt that could dissolve in the liquid. And since you have a liquid reactant, maybe it's that small amount that reacts in the liquid phase and not on the solid surface, okay? And if that's the case, then we can write a mass balance as well. We still have the surface area, but take a look here. What happens is this thing is independent of the solid concentration, because it's not reacting on the solid surface, it's reacting in the liquid phase. And the amount that's dissolved in the liquid phase tends to be a small quantity that tends to be constant, okay? And so we don't even have a diffusion layer necessarily. So this is an interesting sideline. So there we go, we have the dissolution rate, that's what's rate determining, and this is independent of the surface concentration. Okay, so we have two competing mechanisms. Which one's right? Okay, which one's right? So we put this model together, and if you aggregate all of the rate expressions into dimensionless terms, you end up with these parameters here. Okay, so I don't know, it's maybe about 10 parameters. And what we can't do, and this is basically where it gets interesting. So there we have the one thing that discriminates very, very abruptly the two models. If f is 0, you have the dissolution model. If f is greater than 0, you have the shrinking particle model, okay? And so there we have, you know, basically that determinant. That's one of the things we need to estimate, and we have to do it well, okay? Now, this was great. We have that model. We can think about how it works. There are still some simplifications, but, you know, we want to see if it's predictive. So we have to at least know what these parameters are and what we expect to have in the mechanism. Except for now we have a problem. The problem is that we have this reactor, okay, we have batches of data, we have measured inputs, we have measured outputs, we assume normal distributions on the measurements, and we can probably get a good idea of how the instruments work in order to do this, but we have inputs that are basically temperatures, flow rates, the amount of reactant we dump into the reactor at the beginning, and we have very few endpoint concentrations. We have essentially no concentration measurements. So the way we have to do this is entirely by temperature measurements, okay? Which is a little bit weird, you know, because we've got reactions going on and we can't measure anything related to the reactions except indirectly the energy balance over here. The energy balance over here tells us something about the overall rate expressions here in this term and how much heat is being removed with a parameter over there. And that's about all we have, except for some endpoint data. When the reactor is done working, we can see what the product has. That's it. Okay, so we got lots of data, tons of data, but not very informative. Okay, so that's the problem we faced. Okay, so this is basically where we put the problem together. The formulation here is what's called EVM, errors in variables measured. So in other words, we have not only errors in our outputs, the temperatures, and some of the concentrations, but also errors in our inputs, okay, which is basically the, basically looking at the amount of, the amount of feeds that we put in. And believe it or not, they're not perfect. They actually have errors in the actuators and in the scales. So that is our problem. So we're going to put that together. We have the output errors, we have the input errors, we have the inputs and the outputs. And now what we're going to do is put together that parameter estimation and model solution with our direct transcription approach. We have those extra degrees of freedom here, which are basically figuring out the inputs as well as theta. And when you put this problem together, it has about, over 15,000 variables and 14,000 equations. Okay, so this is actually not a tough problem to solve. It's not very big. And this we solved with IPOPT. This was a solution that we got, okay? And what we have with this solution, you can see that these are the estimated parameters. They're scaled. This is the variance, okay? This is basically the diagonal of the reduced Hessian, okay? And what you see is something very disturbing. this parameter, for example, goes to its upper bound. Okay, not much confidence there. And then if you get the relative variance, basically variance divided by the parameter value, we've got some pretty high values. This guy D is very high, okay? And then we have a few others. Okay, now D refers to that boundary layer that's around the solid particle, okay? So this is the diffusion coefficient around there. So now we take a look at this and we ask a couple of questions. First of all, that is a huge number, okay? Huge variance. That one is interesting because that one actually, this number here is also very large, but it actually includes 0 in the confidence interval, okay? That one is a real problem, okay? And so what we have is we have large relative variances for those two parameters and one at its upper bound. Still, that's the fit to the data. You know, I mean, if we didn't care about confidence regions and uniqueness, we look at this fit and say, hey, that's pretty good, okay? So what do? Well, this model is not predictive, okay? So we have to figure out a way to reconcile that by thinking about some model discrimination. So there's the model again, that diffusion coefficient, okay? What if we make an assumption, modify the model and say, let's make that diffusion coefficient, which is non-unique, let's assume that that can be infinite. If that's true, then our boundary layer shrinks to 0, okay? And in that case, we can simplify the problem by throwing out one of these differential equations. In fact, we throw out, we throw out this guy and simply set this equal to that. So we throw out an algebraic equation. The model f, or the parameter f, basically tells us which model to choose from, and we find out that 0 is contained in the confidence interval. And so we choose the dissolution model. And then these three heat transfer coefficients, which are kind of arbitrarily chosen, well, we can find ways to see how sensitive that bound is on the fit to the objective function. And we can think about ways of reparameterizing this heat transfer coefficient. Okay, so let's do that, all right? And so if we use a linearly dependent heat transfer coefficient on temperature, it might look like that, but we have other options too where we don't need 3 parameters to do the fit. So now I have 5 models here based on how I want to choose my parameters, and what I'm going to do with those 5 models is calculate a probability, posterior probability, and I'm going to look at the probability share. Okay, so here are the values of the model. The maximum likelihood functions are here. It takes very little time to evaluate these. The number of parameters is over here. And finally, if I look at the probability share, model 4 is the simplest one, gives me absolutely unique parameters and very small confidence regions, and has the highest probability share. Not perfect, but it's the highest one, okay? And if I look at that, well, then those are the covariances, or the variances here. Confidence intervals are a little bit bigger. Scaled variances are over here. And basically what we end up with is pretty decent parameters on this problem. It's only 5, and there's the fit. Okay, so what you have on the left is the fit to the data, inputs the outputs, and then the measured output basically for the few concentration measurements that we have are over here. So we're happy with that. Is this a predictive model? Well, we don't know yet, but maybe in a year we will. Okay, so this gives us some idea of what we'd have to do to make sure that we can actually extrapolate. Okay, now let me take you to the next case study. The next case study is last thing to say is we did some cross-validation. The cross-validation of this problem, we had 9 data sets, so we basically did estimates with 8, then looked at the 9th one. What we saw was that the parameter estimates and the average of the cross-validation, they were extremely close. If you look at the confidence interval for each of these parameters, you find it's this gray region here, and all of the cross-validated estimates here for these parameters, and these are just 2 samples, are nicely within that confidence region. So we're pretty happy with this result. Okay, good. Now let me go to the next case study. The next case study is kind of interesting because this is where This was a problem from a very large drug company. And what you're going to see here is you're going to see spectra. Okay, so rather than measuring concentrations, what they do is they have spectrometers. Okay, so you have infrared, ultraviolet, visible, and then variations of that. So you can get lots of spectra here. And what you're seeing here is this map here over time and wavelength. Okay, so what you have is a detector at a certain wavelength. You want to find a certain wavelength where you can get good peaks, and then what you do is you tune your instrument to those peaks, either green or red or blue, or maybe all three. And then what you do is you look at the temporal profile. Okay, and that gives you a matrix D, which basically contains all those data with respect to time in the rows and wavelength on the columns. Okay, now our job is to deconvolute those data into a concentration matrix, concentration profiles over time, and an absorbance matrix, basically that tells you how each species independently absorbs in the spectrum. Okay, and then of course there's some error. All right, and the error is kind of an important feature in this problem, because what we're going to see is that, again, we have these matrices over here with time points and wavelength points. We're going to assume this error here. Well, we can assume a certain error that comes to the instrument, which we call zeta, but of course we have modeling error as well in E that contributes also to zeta. So the instrument error is basically due to these things here. The reactor model is also going to have some error, which we'll go into next, and that's basically coming from the way the process is run. Okay, good. So again, we start off with the real spectra. We're basing this on the Beer-Lambert law, okay, which is given up there. And now what we have is a way of saying, okay, I need the concentration matrix, I need the absorbance matrix. It looks like this. And there are several ways to do this, okay? It's usually called multi-curve resolution, okay? And most of the methods that are on this slide here are, well, basically trying to just separate C and S from D. Okay, and this reminded me very much of Yonina's talk, where what you have is you want to basically isolate certain parts of those signals, but they may violate constraints, they may not be real, there may be lots of noise in those signals, and you have to kind of do that. But we also have another thing to worry about, because those concentration matrices, they go back into this model, this bottom model here. So the concentration matrices coming up from here have to work in this model here, and we want to estimate parameters, just like in the previous case study, okay? So now the question is, can we do those two things simultaneously? What we want to do is basically extract the concentration matrix here and deconvolute it so that we get a simultaneous estimation of the concentrations and the kinetic parameters. Okay, this is a tough problem. This is stuff that you can, these methods here are widely available, widely used. There are websites for these. And not to be too pejorative, they're developed by chemists. Okay, so they're happy with that. But then the problem is, once you get your C matrix, you still have to go and estimate the parameters. So now you have this convolution or this mixing of different data structures, error structures, which is a problem. So we start with this problem, and then what we're going to do is we're going to take a look at the disturbances that come from the model, all right? The model itself, you know, you can think of as the reactor model with a Wiener process, okay, or Brownian motion, okay? And so it's really a stochastic differential equation, okay? Now, if you assume that these characteristics about the Brownian motion, okay, that you have essentially a really good initial estimate that is zero, that you have independence in time, okay, so that they're not correlated in time, then what happens is you can make some assumptions with that model description, especially if you assume that those noises are small and Gaussian. And by doing that, you can actually reformulate this into a set of differential equations so that you can actually come up with an exact DAE solution where you can assume a certain level of noise in the model that contributes also to the noise in the signal, but is separate from the instrument noise. And what we would like to do then is we would like to extract the parameters from that model, okay? So that's the idea. So these are some of the transformations that were done for the stochastic differential equations. The model itself has some easy ways of extracting the Brownian motion term, okay? And so once you do that, you can actually take that term over here, plug in some simplifications, and then rewrite this in terms of noise that is actually just the analytic solution or the exact solution of the differential equation. That's basically giving you profiles called Z and Y, and then getting the concentration profile, which is just that exact solution plus the term associated with Brownian motion. Now this takes a little bit of work and derivation. If you'd like to see it, I have a paper that I can send you that goes and talks about it in more detail. So once we know C, we can plug that into this term that multiplies with the absorbance matrix over here and the instrument noise, and then you get D. So now the issue is, if we want to estimate the parameters, we have two sources of noise. We don't know what they are independently. We just know the combined product of those noises. So how do we do that? Well, it's not pretty. Okay, so there we make an assumption here on independent measurements over time and wavelength. What we also have to do is realize that this probability here is going to be made up of the noise of the instrument and the noise in the model itself. And then if we put together a maximum likelihood function, what we'll find out is that we'll have a term here that corresponds to the instrument noise with this variance over here, and then this term over here is going to be the term with the Brownian motion, the variance of the Brownian motion. And then we have the exact model over here. So that's the problem we want to solve. But we don't know what delta and sigma are. So we have to do something, basically expand this problem to include delta and sigma as part of the maximum likelihood. So what we do is we start by doing it this way. We have an initialization estimation roadmap where we apply the optimality conditions for the maximum likelihood problem to include sigma, delta, and another term here, which is basically for the variance, for the absorbance matrix. And so we have a set of optimization problems where we first start by assuming that we know what the concentration is. We solve this model here to find Z. Based on that, what we're going to do is we're going to then determine what S is. This is the whole matrix of absorbances. Once we have that, we're going to go ahead and use that to find out what the concentration profile is. We do this a few times. I'm not saying there's any convergence proof here, but we do this a few times, and then eventually we get enough information where we know C, we know S, we have D, and we can separate the two noise components. This is nice because this is only an initialization. We still have this problem that we solve after that, but with very good starting guesses. So basically that's how we take a look at separating the two. Now, it's not perfect, and I would welcome any suggestions we have, from the audience here on how to simplify that problem, but that's basically what we did. So now to the case study. Okay, the case study is kind of an interesting problem. What we did was we solved several problems, both industrial data and then ones where we made up the data, simulated it just to see the performance. So I'm going to show you a simpler one, which is just is with simulated data. We're making aspirin. Okay, so this is the kinetic sequence, the reaction mechanism for making aspirin. What you do is you start off with salicylic acid, reacted with acetic anhydride, and you form acetyl salicylic acid and acetic acid over here. Okay, so this is the main reaction, but you have side reactions. Okay, and you want a predictive model to reduce the amount of side products. For example, this one, ASAA, acetyl salicylic anhydride, you don't want. Okay, you don't want that in your aspirin tablet. There's degradation of, for example, forming acetyl anhydride to get acetic acid. And then, of course, what you have over here is two things that are not really reactions. What you're going to do is you're going to take the salicylic acid as a solid, dissolve it to the liquid, And once you create the aspirin, the ASA, acetyl salicylic acid, that has to be crystallized as a solid or precipitated. So that's basically the idea. The rate expressions are given here, okay? And now, of course, what we have to do is get those parameters, all right? And what we have here is we have spectra. The spectra matrix is over here. This is the size of that matrix. This doesn't take very long. First of all, getting around these loops is about 83 seconds. And IPOPT then solves the full problem in about 10 seconds. So these are the estimated and the exact values because it was a simulation. We got very good error estimates over here. These are a little high over here with the relative errors, but still acceptable. And that gives you some idea of how it works. Now, let me mention that everything that we did in case study 1 will still appear here in case study 2 with model discrimination. But now we have the entire problem of actually working with the spectra and trying to deconvolute those as well. So that's basically the next thing that we actually had to worry about. There are many other examples that we solved here. And actually one of the things that we were very happy about with our partners is they said, wow, you can get this level of information with just spectroscopy. I don't have to buy an NMR, I don't have to buy a mass spec, I don't have to get a much more expensive equipment because I can't see all of these measurements. Instead, I can get enough out of these measurements to get some idea of how to build a predictive model. Okay, and so that's kind of the thing that they're after in the end. Okay, good. So that was the second case study. And what I'd like to do to wind up is to talk about, well, first of all, the aspirin case, just to give you some idea of now what the concentration profiles look like. You can see these are the error bars in the concentration profile. This is basically the production of the acetyl salicylic acid over time, okay? And you can see how well it actually works, very small deviations on the concentration profiles. Okay, now, the last thing I wanted to talk about is the why, okay? We have the how, we have the what with the case studies, and the why. Why do we do this? Why are we actually interested in getting really good parameter estimates and discriminating among different models so we get a really good predictive model? So I'm going to talk about the last case study, which is a fairly interesting process, okay? This is where they actually ended up with a very detailed model and one that was validated extremely well in practice, okay? So this is a process that makes polyols, okay? So if you're wondering what a polyol is, it's a polymer that's made out of very reactive monomers, and it's used to make polyurethanes. So everyone here knows what a polyurethane is because you're sitting on it, okay? It's foam, okay? It's made by a very large manufacturer of polyurethanes, and this is the process. What you have is you start off with epoxides, molecules that looks like this, okay? And you react them with alcohols, you have a potassium hydroxide catalyst, and now you're putting this into a reactor, and the most important thing in this reactor is this cooler, okay? Because what happens here is you have a nitrogen blanket over here, you feed in the monomer, it reacts with a catalyst, you have to remove heat, and you react it under high pressure, okay? And now what happens is if you, at any point in time, you lose cooling, it's going to blow up, okay? And this is what they're the most afraid of. So if there's enough residual reactants, residual monomer in there, when you lose cooling, it's going to blow up. So the question is, how do you feed this mixture? And how do you react this thing and set the temperature profiles so that you get, you can react your batch in minimum time, okay? So this is something where they developed an extremely detailed model. They validated it with tons of data over several years, and they came up with an operating policy, okay? And we thought, well, good. Now this is a dynamic optimization problem. Here is the kinetic mechanism. What makes this challenging is that all of these rate constants, this is the set of all rate constants, okay? It's a stiff problem. These reactions happen much faster than all of the others. And now you see the subscripts here on each of the species, N. That refers to the number of units in each polymer chain. N can go up to several hundred. Okay, so those are all the species that are in the reactor. Now, there are ways to reduce this model, but the point is you have to keep track of all of them because the molecular weight distribution of this polymer determines the quality of the product. It has to meet a certain spec when you're done. Okay, so this is the species. You have basically water, monomer M, you have dormant polymer D, you have growing polymer G, and you have side components Q, which you don't want, byproducts. All right? So those are the things that actually are part of the system. This was put together by a very nice DAE model, reaction model, and this is how it validated in the plant. Now, this is only a cartoon to give you some idea of how well the data fit. And this is the pressure profile over time compared to the plant data. Over here, there's some deviation, but it doesn't matter because the reaction's pretty much finished, so they don't care what the nitrogen atmosphere was like. But this is where the model was tuned to the plant and was pronounced predictive. And they had other ways to pronounce that predictive, but nevertheless, that was the predictive model. So the question is, if you now solve this as a large-scale optimization problem with direct transcription, what difference does it make? Well, there's the optimization problem. What you have is the process model, the quality constraints that tell you what the product has to look like, the safety constraints, and in particular, this great constraint of saying, if I lose cooling at any point, what's the endpoint temperature going to be so it doesn't blow up? Okay? And then we have control variables, reactor temperature, monomer feed, and our solution strategy is direct transcription. Here's the result. The blue line is how they optimized it in the past. Okay? Those are the profiles, and what you can see is this is normalized time. There's the temperature profile on top and the feed rate on the bottom. Now, the interesting thing is they're very conservative because if they know they get this wrong, it's going to blow up. Okay? So what we did was when we did our optimization, it gives you the red line and basically saves us about 42% in time. Okay? This is a big deal because actually it turns out to mean a lot of money. What's the difference? And in fact, the question they asked is, well, we already optimized it. What did you do differently? Well, the Optima actually has an interesting explanation. If you take a look at this, instead of feeding at a low temperature with a low amount of reactant, we feed at a high temperature and a rather high amount of reactant. And then what happens is a constraint kicks in right about here. I'm sorry, I can't, out of battery. Okay, right about 0.5 or 0.05. And then it rides that constraint until it reacts all of the monomer, and then at that point, it kicks up the temperature again, and then stops and makes the product, okay? Now, it turns out at that point, the reaction's done. It satisfies the specs, and let me show you what happens. That's where it rides the constraint, the cooling constraint. There is this other safety constraint up here that it barely hits in case you lose cooling. It's kind of artificial. And then what happens at the end is that, okay, now you're done with the cooling capacity. This is where you can increase the temperature, and basically it goes past to what happens. These are all the specs of the product at the end, and you can see even though it took much less time, all of the specs were met. Okay, now this is not the end of the story, because this is only one reactor that was in the middle of a much larger process. The whole point was not to see this specific result. The whole point was to say, wow, we can now do a fast optimization anytime our conditions change in the plant, anytime our cooling goes down, anytime we have to share resources, anytime we're in oversold or undersold capacity. And so that becomes part of the planning system and the control system to have this thing re-optimized at will. Okay? This result, the ability to do that, is worth about $5 million a year in that one plant. Okay? That is the value of the predictive model. And so getting that right means that you can do optimizations like this. Getting it wrong means that the optimization is just an academic exercise that nobody will believe in the plant. So that's basically the whole point of thinking about these first principles models, then using statistics and optimization to run these things. So let me stop here and say the following. First of all, parameter estimation and model discrimination and with first principle models is what we talked about. We start with maximum likelihood formulations and normal measurement error distributions. So fairly reasonable assumptions that are, well, lead to tractable problems. We've got optimization-based tools based on parameter estimation, giving you statistical inference, and then using that for probability shares to look at classifying alternative models. And finally, I hope you were interested in the challenging case studies, okay? The idea of saying, what can you do with non-informative data? Can you still discriminate among models and use something that we hope has reasonable predictive capability? Can we deconvolute spectral distributions and still use them for parameter estimation at the same time and basically make sure that we have separated the instrument error from the model error? And finally, once you have a validated model, you can ensure predictive optimization models. And with good optimization tools, you can extrapolate where you weren't before. So thank you very much for your attention. If there are any questions, I'd be very happy to answer them.